So considering a TSP, we have to make it stationary. So we will detrend it. Okay. Now here I am giving the manual operation of detrending.
Yeah.
So suppose we have a particular variable, and that variable we have to regress on a trend. We are getting this trend, and then that variable value minus this trend, that is the estimated trend, will give us the, this is the fitted series 1.39 plus 0.5t. Then putting the t values, all the t values, we will get the estimated yt value. Then that this yt minus this yt estimated value will give us the detrended value. So this is the detrended series. Okay, this is what we do manually. But as I told you earlier, we can do it in another way also, using the Frisch-Bock theorem. So Frisch and Bock in 1933 suggested that if we include a time trend in a regression, that is equivalent to detrending all the variables by regressing them individually on time. That is what I told you earlier. This is the famous Frisch-Bock theorem in the context of multiple regression. So this is so with this is not only for detrending. We actually, what we do in a multiple regression framework is we are controlling for the effect of other variables. If we want to have the marginal effect of one variable on the dependent variable, then we control the effect of all other variables. So that controlling is like detrending. So that is the idea of this. Now, suppose we have two time series. For example, consumption series and the income series. And I have a usually we know if these two data series are over the time series data sets, then naturally we have to deflate both the series, right? Then only we use the deflated series in regression. That is, in a time series regression, all the value terms, if any variable is in value term, then we have to detrend it. Then only we can use that variable in a time series regression. In a time series regression, all the time series variables must be deflated value if they are in value terms. But we need to do the deflation manually according to Frisch-Bock theorem. What we need to do there? Can anybody tell me? How can we deflate all the series without actually deflating, prior deflating them? Anybody? What shall we do? Anybody getting any idea? No?
Sir, can you please repeat the question,
Yes,
sir?
the question is, suppose we have in value terms consumption and income. We are fitting a regression, right? But this is over the time. We have time series data. And we know that in a time series regression, then we should use deflated series only. That is, we have to remove the inflationary effects from both consumption and income series. Then those deflated series we have to use in regression. That means before doing the regression, we have to deflate the series. That is the prior need. We have to deflate them. Then we do the regression. But according to friction work, we need not do the prior deflation. Rather, how can we do the regression in that case? That is, we are using the nominal values of consumption and income. How
Sir,
can we
what
make it in real terms?
So what
how-
about the
how we
vol?
do?
Sir, what about the volume, sir? Volume is already a deflated one. So
What is
if in
volume? I am not,
sir, if in
I'm not
if
using
it
any
is
volume.
oh,
I'm not using any volume, but I have consumption. Okay, consumption
okay,
expenditure.
okay.
Yeah, consumption expenditure in value terms, in rupee terms, income in rupee terms, and this is time series. Since they are in time series, we know all the nominal values includes the effect of inflation, right? So to do so that means we are having a data set in nominal terms, value terms. We cannot have a time series regression with the value terms or nominal terms. We have to use the real value terms. The variables must be in real value terms. So we will get the real value terms from the nominal value terms by deflating the nominal values. We remove the inflationary effects, so the nominal values will become real values. So with the real value variables, only we can do the regression. But according to the Fishbone theorem, we need not do the prior deflation. We add some variable in the multiple regression, and then everything will be taken care of.
Sir, is it disposable income?
Can you tell me how?
Hello?
Yeah, disposable income or whatever be disposable income, but it is not in real things. That is the problem.
Correct,
But
correct, sir. Because
in a regression, we have to use real things. What is it?
my expenses always depend upon how much I have in my hand. It is an absolute figure. Because when it comes to the figure, even for example, for 100 rupees, 10 rupees is 10%, and for 1000 rupees, 100 rupees is a 10%. But while 10 rupees and 100 rupees in percent term look same, but the purchasing power of 10 and 100 are totally different. So that is the reason we require absolute value or nominal value compare with respect to the percentage terms. This is what my opinion is.
But no, my question is different. Now see, if we are using nominal values in a regression, the regression coefficients are inflated ones because the nominal values include the effect of inflation also. So we have to remove the inflation from that is, we have to deflate the consumption expenditure series and income series. And then using these deflated series, we do the regression. That is the real regression. That is regression on real terms. That is the real regression. So how can we do that without deflating initially the nominal values? In the regression equation, in the regression framework, we are using nominal values. But along with the nominal values, we are using some other variable so that we will get the result of deflation automatically. Any idea you are getting? See, take the case of this particular one. How do we detrench? In a regression, how do we detrench? We are including a time trench in a regression, that is T, time, 1, 2, 3, 4, 5. That time we are including in a regression. In the presence of that time variable, will detrench all the variables in the regression. Similarly, if we have consumption as a function of income, consumption expenditure, consumption expenditure, then income. Along with the income as an independent variable, we include another variable so that both the consumption variable and income variable will be deflated. So which variable we will use?
Sir, is it the price index or something like that?
Of course, the price index. Either we use the price index or we use the inflation rate as such. Good idea. If we include an inflationary term, inflation term in the equation along with nominal values of consumption expenditure and income, then the regression will be all real terms because the presence of inflation will deflate both consumption expenditure and income, so that we will be getting a real regression. So that means we did not go for deflating the time series values. First, we just include an inflationary term, either a price index or the inflation term as such. That will deflate all the series, all the value terms within the regression. That is the beauty of Frisch and Vogt theorem. So, good idea. So hereafter, if you want to find a time series, in a time series, you have say for example returns. You have returns over the time. You have to find, if you want to find the real returns. Similarly, you have exchange rate. If you want to get the real exchange rate, then along with the return, nominal returns and nominal exchange value, you put a regression, you put a inflation variable, either the price index or the percentage change of that or the log difference of that. Then the regression will be about the real terms of returns, real returns and real exchange rate. So that is the Frisch-Vogt theorem. Got it? Now the residuals we get from including a time trend is usually interpreted as the cyclical components in business cycle theory, or we use it for estimating the trend growth rates. Okay, is it clear? I think so. Okay. Now, so we know that for a stationary series,
Hello, sir.
we have a zero mean, and if we have an intercept, then the mean value will be equal to that intercept A. Then variance of y is a constant, covariance also is a constant. They are all independent of time. That is the property of a stationary process.
Sir, hello.
Now, hello.
Sir,
You have any
please
doubt?
explain- Sir, can you please
What is
explain
it?
how? Sir, hello.
Ah,
Sir, I didn't get the point, sir. How to use the values in real terms while regressing income on consumption? You said.
we are regressing consumption on income. Okay, the
Yeah.
consumption expenditure is in money terms. Okay, and income also is in money terms. That is what we say value terms, right? And if we have the time series data, over the time we know the prices are increasing. We have inflationary
Inflationary effect in that.
Yeah, so the consumption expenditure and income series will be including those inflationary effects. Got the idea?
Yes, sir.
Yeah. So if we regress these nominal value series, then the estimates that we get will be inflated because of the presence of inflation. That
Yes,
is not
sir.
the real, that is not the real estimate. What idea? So
Yes,
we
sir.
have to remove, we have to deflate, we have to remove the inflation from this series. That is, we have to
Hmm.
deflate it.
Yes, sir.
So to get the real regression, we have to use deflated series. Now earlier before Frischwald came to the scene, earlier econometricians were doing a lot of calculations like this. That is, first they will deflate one series, then they will deflate the other series, then using the deflated series, they will do the regression. Now, Frischwald told them that this double work is not needed. We can do one regression by including inflation or price index in the
As a
regression
dependent.
equation. Yeah, it will be all the variables will be deflated.
But sir, there will be a simultaneous problem again. There may be the possibility of multicollinearity between the variables.
See, in a time series, regression, sometimes there may be the problem of multicollinearity. But remember, multicollinearity is not a major problem. We can just close our eye towards that, right?
Yes, sir.
Yeah. Okay. What is it? Somebody was asking.
Sir, I have a
Ah.
question. Do you mean to say in
Ah.
the time series analysis, we don't have to worry about the multicollinearity when we do a multi-regression?
Multiple regression. Right. You
So
remember
we,
in the last class in the last class I showed you an example, right?
yes, sir.
See,
Yes, sir.
if there is any serious multicollinearity problem, what we have to do is we remove one of the variables, right? But
Yes, sir.
sometimes if we remove the variable, the model will not become adequate.
Okay.
We will have the specification problem.
Right, sir.
So the specification problem is more dangerous than multicollinearity problem in consequences. So we have no other way than ignoring multicollinearity. That is why it is given as the last one. Just ignore it.
Okay. Okay, sir. Thank you.
Right.
Sir?
Ah.
Yes, sir. Sir, one thing, can you explain, sir? Every time series is either a TSP or a DSP. So,
Right.
so for every time series, we have to first detrend it and then we have to estimate it, sir.
Now see, every time series may be either a DSP or a TSP or both. Okay.
Yes, sir.
Okay. In DSP also we can have a deterministic trend. So in finding unit root, therefore we will have several options. If we have a trend, then we have to remove the trend and find whether there is a unit root or not. There are some options. When we come to the unit root case in the workshop, I will show you that.
Okay.
So we have
Sir,
that means we can
and
detrend
sir,
it by including a time variable. What is it?
Sir, and you will show us in Gretel how to detrend it, no, sir?
Oh yes. We will do in the afternoon that.
Okay,
The
thank
unit
you,
root
sir.
test and cointegration, everything I will show you.
Thank you, sir.
So if there is any trend in a variable, first we have to detrend it. For detrending in the unit root test framework, we include a time trend that will detrend it, right? Thanks to Frischwald theorem. Yeah, so that procedure is there. That I shall show you. Okay, now Now let us see the consequence of unit root. Why non-stationarity is a problem in regression. Now we know that as stationary time series we can express in terms of a regression model with fixed coefficients. So the coefficients are to be considered fixed. However, the OLS estimator in the presence of a unit root cannot have an asymptotic distribution. See, asymptotic distribution means the distribution of the OLS estimator as time increases infinitely. Asymptotic means as time increases infinitely. Now, why we say that the OLS estimator in the presence of unit root does not have an asymptotic distribution? Now we know that the OLS estimator from a regression of YT on XT, we can estimate using the ratio of covariance of YT and XT divided by the variance of XT. That is the formula. Covariance divided by variance of XT. Now, suppose YT is stationary variable and XT is non-stationary variable. Then what will happen? The OLS estimator from the regression of YT on XT will converges to 0 asymptotically because variance of XT is a function of T and it increases infinitely with time. We know that. For a non-stationary variable, variance of that variable is a function of time. Here XT is non-stationary. If XT is non-stationary, then its variance is a function of time. And in the OLS estimator equation, covariance divided by variance of XT, this variance of XT will increase with the time, over the time. As time increases, the variance of XT will also increase. And the regression coefficient will theoretically, okay, theoretically it will converge to 0. It cannot be considered a fixed coefficient. But a regression, in the regression framework, we need a fixed coefficient. Theoretically, this is not possible if we have a non-stationary variable in our regression. So that is why we say that the OLS estimator does not have an asymptotic distribution. Got the idea?
Sir, sorry
Okay.
to interrupt.
So
Sir,
no,
sir, sorry to interrupt over here.
Yes. It's
Can
okay.
you,
It's okay. No problem.
Can you please explain this with an example, sir? Like one variable which is stationary and a non-stationary variable. With an example, if you can explain, I think that would be more clear.
Suppose you see most of the macroeconomic variables are non-stationary. Stationary variables are very rare. Some of the variables are there, but most of the variables are non-stationary. If we have both the variables non-stationary or one of the variables non-stationary, then we will have this problem. Because either the covariance will be increasing over the time or the variance will be increasing over the time. In both the cases, theoretically, the OLS estimator cannot be considered constant, fixed. What idea?
Yes, sir.
Is it clear?
Yes, sir. So you mean to say that if we take macroeconomic variables, most of the time they are non-stationary. But if we are taking any stock prices of a company or maybe a stock indices, if we take, then it could be stationary. And then during that time, we are going to check the. I mean, this OLS estimator cannot.
See, whatever be the case, if we have a time series variable, we have to see whether there is a unit root in that variable. If there is a unit root, then there is a problem with the regression like this. So we have to remove the unit root. We have to remove the unit root.
Right.
That is the idea. So usually the stock price index is non-stationary, and if we take the difference of that, log difference, that is the returns. The returns are usually stationary.
Okay, sir.
Okay.
Now I understood. Yeah.
So this is the consequence of the non-stationarity. We cannot expect a constant or fixed OLS estimated from the regression of non-stationary variables. Now I am giving an example. This example is widely quoted one, and this particular example as a Monte Carlo experiment was done in 1974 by two econometricians, Granger and Newbold. I will come to them after some time. Now, suppose we have two unrelated random walk processes. That is YT. See, the coefficient is equal to 1. The root is equal to 1. And the error term, random error term is independently and identically distributed as a normal variable. Similarly, we have another one, xt, another random variable where the new error term is yt, random walk. Okay, so we have two random walk processes. Now, along with this, we have an additional assumption that the covariance between ut and vt is 0. There is no relationship between these two. If there is no relationship between these two, then yt and xt must be unrelated. They must be independent of each other. Okay. Now, suppose we fit a regression of yt on xt. We are fitting a regression of yt on xt, and we know that yt and xt are two unrelated random walk series. There is no way we can have a valid regression. But now what will happen? We know that if there is no relationship between yt and xt, the R squared from this regression must be around 0. It must tend towards 0, close to 0. But what will happen when we do this? Here, I am giving the example. I told you it was the 1974 Monte Carlo experiment by Granger and Newbold. They got very high R squared and highly significant t values. That is an R squared value very close to 1 and very, very high t values. That means the regression as a whole is highly significant statistically, but they got a very low DW statistic. But where do we use the DW statistic? For finding whether there is any autocorrelation among the residuals or in the error term. That is whether the no autocorrelation assumption of the error term is violated. To test that, we use the DW statistic. Here they got a DW statistic that is close to 0. Now what they did is they run the regression in first differences. That is, they difference both yt and xt, and we know by differencing they become stationary. Now what happens is when they regressed it, the differences, they got an R squared value close to 0 and the DW statistic close to 2, indicating there is no autocorrelation, the model is adequate. R squared close to 0 means that there is no relationship between yt and xt, what we expected. So the high R squared that we obtained earlier was just spurious. So the earlier regression was a spurious regression. So Granger and Newbold suggested that whenever we have a case where R squared is greater than DW statistic, then we have a case of spurious regression. That is invalid regression. We cannot depend on that. That is, we have to make the series stationary and then do the regression. Then only we will get the valid regression. So this is the case of the spurious regression I told you earlier. You remember the last day I told you about the spurious regression. So remember this particular suggestion by Granger and Newbold. That is, whenever R squared is greater than DW, the equation is spurious. Now, next time when you attend any seminar and somebody is presenting a paper with a very time series data, very high R squared, and we know that whenever we have a very high R squared, we will be very happy because the model explains our model explains the variation in the dependent variable very highly. So we will be very jubilant about that. So getting an R squared is very much happier for us. So next time when you attend a seminar and somebody is reporting on very high R squared, ask him what is about the DW statistic. I told you earlier, there is a practice of not doing or not reporting the results on the model adequacy test. One must do that first. At least the DW statistic must be there, so that we can find out whether the model is not suffering from auto-regression. So next time you ask him, where is your DW statistic? And ask to compare that. And you have to educate him if the R squared is greater than DW statistic, that the result you obtained is a spurious one. It's nonsense. Now, actually, there is a difference between nonsense regression and spurious regression. I shall come to that shortly. It is here. Is it spurious or nonsense regression? Now, there is a long-standing puzzle over high correlations between what ought to be unrelated time series variables. For example, the high positive correlation between the murder rate and membership of the Church of England. This was the study done by Yule in 1926. I told you about George Eugene Yule, from whom originated the auto-regression process in 1926. So in 1926, he did a study on the correlation between the murder rate and the membership of the Church of England. He collected time series data on murder rate and membership of the Church of England, and he got a very high positive correlation between the two variables. Now, can we take that high positive correlation in its face value? So there is a problem, right? We cannot expect a positive correlation between the murder rate and the number of Christian devotees of Church of England. And therefore, he classified the correlations or regressions in two types: nonsense regression and spurious regression. And nonsense regression is the one that we get from the integrated but mutually independent time series. That is, we have high serial correlation in each series, very high correlation. The spurious regression we get with the variables depending on a common third factor, such as a linear trend. So, what Granger and Newbold called a spurious regression is actually a nonsense regression in the language of Yule, because the so-called spurious regression of Granger and Newbold is obtained out of integrated time series. because of very high serial correlation among the residuals. Got the idea? And spurious regression happens when the variables, all the variables are depending on a third factor. That is some other factor. For example, a linear trend. In the case of the above one, that is the high positive correlation between the moderate and the membership of the Church of England. In both the cases, we have a linear positive trend. Moderate is increasing over the time. There is a positive trend. Membership of the Church of England is increasing over the time. There is a positive trend. So the correlation that we get between these two variables is actually the correlation between the two trends. Now, what Yule did is he removed the trend from these two variables and he got
Hello, sir.
a close to zero correlation between the variables.
Hello, sir.
Got the idea?
Sir, in the example you said, sir, in the example you said that income and consumption, when we are regressing consumption on income, there is a common factor that is inflation. If we consider inflation as an independent, if we consider inflation as an independent variable, then the problem is solved.
Yeah, that is we are deflating both the series.
Exactly. If we do not consider inflation as an independent variable, will it be a problem of spurious regression in that case?
Of course, because see, if we find that there is unit root in the series, then it is then both the series are integrated. Got it? All the series are integrated. So there is a problem of nonsense regression in Yule's language, or spurious regression in Granger-Newbold language. Actually, these days in time series econometrics, these two differences are not kept. Both the nonsense regression and spurious regression are used, these two terms are used interchangeably. So in general, instead of the nonsense regression, we are following the Granger-Newbold terminology. That is the spurious regression. Actually, there is some difference between these two. The spurious regression, usually we get if there is a third variable affecting the two variables. A other factor, a third factor, or we say other factor. The nonsense regression we get from the integrated non-stationary series. But unfortunately, we do not distinguish these days between these two cases. We say spurious regression, and that is related to only the integrated one. The other one we are not considering.
Sir,
What
I
idea?
have a second question.
Is it clear?
Sir, yes, sir, yes, sir, it is clear. Sir, you are saying that income and consumption are somehow integrated. Sir, should they be integrated of the same order, or they may be integrated of some other orders even?
Maybe we have to check for the order of the integration. We have to do the unit root test. Okay. So otherwise we cannot tell. Usually the national income figures in some context, in the case of some countries, the national income or the consumption series are integrated of order 1, but in some cases we find that there are 2 unit roots. So it varies. So we have to see whether that is first we have to see the order of integration. Okay? Yeah. Right? Okay. Oh, yeah, right. So now here I am giving an example, income and consumption. So here we are regressing consumption on income and getting, see the p values are 0. That is, the t values are very, very high. So we are getting a highly significant model. And asteroid is 0.9975. So one will dance if one gets this particular asteroid. It's very close to 1. And the F probability value also is also is 0. But the question is now, see the Durbin-Watson test. It is 0.68. It is 0.68. And that is less than our asteroid. So this is nothing but a spurious regression. Anyway, I wanted to ask you whether this regression is a spurious one, or whether there is a genuine long-run relationship between these two variables. I have already told you the case. It is a spurious regression in the language of Granger and Newborn. Otherwise, it is a nonsense regression. Now, if we first difference both the variables, now see the probabilities are very, very high. The p-values are very, very high. R-squared is close to 0. And the DW statistic close to 2. The model is adequate. But there is no relationship between the two variables as expected. So this is the case of the spurious regression. Now here we have the time series plot of income and consumption. And here we have the differential variables. Both income and consumption are non-stationary, and delta, the difference series are stationary. So it is very essential that we check for stationarity of the time series. The classical approach of evaluating stationarity is, as I told you earlier, in terms of the autocorrelation function, that is ACF, the hologram. If we have fast decaying ACF, that's an indication of stationarity. The modern procedure is to go for unit root tests. We have Dickey Fuller test or augmented Dickey Fuller test, then Phillips Perron non-parametric test, and so on. We have a large number of unit root tests, maybe more than 100. But some of these tests are available in packages, especially the ADF. Usually we do this ADF, even though for all the tests, the power is very, very low, as expected. Now about the parallelogram, I have already given some indication of parallelogram earlier. So this is a stationary series because the autocorrelation coefficients are fast decaying, and in this case they are not fast decaying. Here also we have fast decaying. Okay, this is a non-stationary time series. ACF is very slowly decreasing. So up to this lag, it is not decaying. Okay. Now there is a question of choice between differencing and detrending. We have seen that if we have a DSP series,
Sir, actually, I gone through a paper of Madala and Wu. In that paper, sir, they have said that like Philip Perron and ADF tests are not that much powerful tests of testing a unit root. They suggest rather using an NG and Perron test and other tests are more useful in compared to them. But they don't provide any rigorous discussion on that how NG Perron test qualifies better than the ADF or PP test. Sir, can you emphasize on that particular issue?
See, as I told you earlier, most of the tests are with very low power. Even this tests or KPSS. Unfortunately, the tests that you cited are not available in any package. But to some extent, the KPSS there is a test with the null hypothesis of stationarity. In all other cases, we have the null hypothesis of
Of a
non-stationarity.
unit root.
The KPSS test has a null hypothesis of stationarity.
Hadri element test, sir.
And this is a
Hadri
parametric test.
element.
So I told
Yes, sir.
you we have a large number of tests, but only a few are available in the packages, and those few, actually all these more than 100 tests are with very less power, very less power. Whether we take ADF or PP or KPSS, all these tests have very low power. We know,
Sir, in
actually we know, whenever we specify an alpha significance level, then corresponding to that, there is a loss of power, right? The problem is there. We are fixing the alpha or the significance level initially, and we are going for only very low alpha. And very low alpha means very low power also. So every statistical test has this problem of the trade-off. There is a trade-off between power and size. Size means alpha, the significance level. There is a trade-off between these two, and that trade-off cannot be actually eliminated. If you go for a small size of tests for alpha level, significance level, then there will be then the corresponding beta will be very high. Beta is the probability of committing the type 2 error.
Yes, sir.
Type 2 error, that will be very high. That means the power of the test will be
Reduced.
very low.
Power of the test will be
So
reduced.
it so happens. Since we do not have a powerful test, we have to be satisfied with whatever is available through our packages. That is the problem. But now remember, in R, there are provisions for writing a program of your own with a high power. But with the high power at the same time will have a high alpha level also. That is the problem, because between these two, there is a trade-off. Okay?
Yes, sir.
Okay.
Okay, sir.
Now we know that whenever we have a DSP, we have two difference. Whenever we have a TSP, then we have to detrend. Okay? Now, we have to make a discrimination between TSP and DSP models. Whether the root of the series is equal to 1 or whether it is less than 1. Whether the series is integrated or not. And that is the significance of the uniroot test. Now, I shall tell you some history about the uniroot test. The first ever attempt at a uniroot test was done by Nelson and Prosser in 1982 using the augmented Dickey-Fuller uniroot test. Their null hypothesis was that a time series belongs to different stationary process class against the alternative hypothesis that it is a TSP, trend stationary process. And they carried out the augmented Dickey-Fuller test on 14 US macroeconomic time series. And they found that 13 out of the 14 belong to the DSP class. The only exception was the unemployment rate. These are the variables that they used. That is real GDP, nominal GDP, real per capita GNP, industrial production, employment, unemployment rate. Unemployment rate was the only one where we reject the uniroot null hypothesis. All others do not reject the uniroot null hypothesis. So this Nelson-Prosser data, this particular data set has become a guinea pig for all the uniroot test makers. All of them used this particular data set. Now see the sample size. For example, industrial production, they have used the 111 annual data. In all the cases, they were using the annual data. Consumer prices, more than a century. Velocity of money, that also more than a century. And so, so naturally we know that there is some problem with the data sets. There may be some break in the series, especially when we are using large data sets, say 111. We have data on industrial production during the period of the Great Depression also. And Great Depression is a break point. And that is how Perron later on came criticizing Nelson-Prosser research, telling that this problem, the non-stationarity research that they got is actually a misleading one, because if there is a break in the time series, then that can generate a pseudo non-stationarity. So the non-stationarity that Nelson and Prosser found in most of these time series, according to Perron, was because there was or there might be a break in the series. So then a lot of other studies also found, and Perron came out with a new uniroot test with the break, and he used the exogenous break. So he used a chunk test, and then there came endogenous break test, and so on. We have a large number of uniroot tests these days, including recognizing the break. So in general, if we have a non-stationary series, then we have to run the regression in first differences. And this is the procedure used in the classical ARIMA modeling. So they see whether there is a unit root in the series, and if there is, then they will difference the series, and on the difference within the different series, they will do the estimation in terms of the ARIMA. Or we have another method, that is we check for cointegration among the series, because we have some problems with the difference. So in the classical approach, we have to difference the series, and later econometricians found that there are some problems with the difference. What are those problems? By differencing, actually, we are losing something. What are we losing? We are losing the long run information. So the modern econometricians were telling us that solving the non-stationarity problem via differencing is equivalent to throwing the baby out with the bathwater, because differencing results in valuable long-run information being lost. So we will get the long-run information, valuable long-run information, only if we do the regression with the level variables, yt on xt. If we differentiate and do a regression of delta yt on delta xt, what we are getting is a short-run regression, not a long-run regression. And in a short-run regression, we do not have the long-run information. That is the problem. Now, most of the economic financial relationships in theory are given in terms of long-term relationships, not in terms of short-run ones, between the variables in their levels, not in their differences. We say that consumption expenditure depends on income. we do not tell that change in consumption expenditure depends on change in income. So we have the long-term relationships among most of the economic and financial relationships. So we are faced with two seemingly irreconcilable objectives. We have to avoid spurious regression of the integrated variables. At the same time, we have to conserve the long-term relationship. If we want to conserve the long-term relationship, we have to regress, we have to have a regression with the level variables only. But the level variables are integrated variables, and a regression with the integrated variables will be a spurious regression. So we have an irreconcilable problem. If we want to avoid spurious regression, then we will not be conserving the long-term relationship. If we want to conserve the long-term relationship, then we will have a spurious regression. That is the problem. So what we have to, and because of this came the new concept of cointegration. That is, suppose we have two variables yt and xt. Yt may be deterministic or integrated. That is, deterministic means stationary, integrated means non-stationary. Similarly, xt also can be stationary and non-stationary. If we have both yt and xt stationary variables, then we have a valid regression. Otherwise, in all the cases, we will be getting spurious regression. If one or both the variables are integrated, then we will be getting spurious regression. But if both the variables are integrated, then we have a qualification. The regression will be spurious unless they are co-integrated. That means if yt and xt, both integrated series, if they are co-integrated, then the level variable regression between the two will not be spurious. That is the case. That is co-integration. Okay. Now, what is this co-integration? Suppose we have two variables, income and consumption. Both are increasing over the time, and both are non-stationary variables. Now, if we get a linear combination between income and consumption, what will be the linear combination between income and consumption? For example, income minus consumption. That is savings, right? So we have a linear combination of the two non-stationary variables. This savings also may be non-stationary, but in some cases, some contexts, the linear combination savings may be stationary. If the linear combination is stationary, then we say that income and consumption are co-integrated. In that case, we can have a valid regression with the income and consumption in the level variable itself. We did not go for difference. That is the idea of co-integration. That is, if a linear combination of two non-stationary series becoming stationary, then we have the case of co-integration. Now, in this particular case, the two variables are moving almost together, and that togetherness tells us that they are co-integrated. That is, co-integration also implies that the position of one variable will tell us the position of the other variable. So at any level here, the position of consumption will tell us the position of the income variable. And that is cointegration. So if two variables are non-stationary, they seem to move together if they are cointegrated. So this concept of cointegration was put forward by Granger in 1981. This combines both the short-run and long-run perspectives. So if there is an equilibrium relationship between two economic variables, they may deviate from the equilibrium in the short run, but they will adjust towards the long run, towards the equilibrium in the long run. That is the concept of cointegration. That is, it is a stationary combination of non-stationary variables, as I have told you earlier. Actually, the interpretation of this one, that is, they may deviate from the equilibrium in the short run, but will adjust towards the equilibrium in the longer one, is the basis of Granger's representation theorem. That Granger's representation theorem in 1981 combines both the short run and the long run. And this is in terms of what is called an error correction mechanism. So this adjustment towards the equilibrium in the long run is the error correction. That error correction will lead the short run disequilibrium into the long run equilibrium. So that is the idea of Granger's 1981 representation theorem. Now, as I told you earlier, the same one. We have the data on income and consumption over a long period of time, and their difference, that is the linear combination of income and consumption, that is saving, also may be upward trend, also may be having an upward trend. But a property of I1 variables is that sometimes their linear combination may be an I0 or stationary variable. If it is so, then we can say that YT and XT are both cointegrated. So this I have already told you. Now, we have two examples. The first one is about a drunk and her dog, an illustration of cointegration and error correction, written by Murray and published in the American Statistician in 1994. This is the case of a drunk woman, okay? And she has a dog. She is drunk, therefore she has a random walk. She is an integrated process. Her movement is an integrated process. The dog's wandering also is a random walk. So its movement also is a non-stationary series, integrated one. So we have two random walk processes. But actually, these two will have a cointegration. How? Because both of them have random walks, even though the drunk woman is wandering here and there, and the dog also is wandering here and there. Both of them will go together. The drunk woman often will call. See, the dog's name is Oliver. Okay, so she will call, Oliver, where are you? Oliver, where are you? Hearing her voice, the dog will come back to her, and they will move together. So whenever they drift apart, either the drunk will call Oliver, or Oliver will sense that, oh, my master is drifting away from me. I have to be with her, otherwise she will what? She will do something. Okay. So the dog will go with her, even though both of them are in their random walks. So this article is available in the net. You can freely download it and have a read. It gives this particular example very simple language, but with some equations. Then after that came another article, a drunk, her dog. Now a boyfriend also is added. An illustration of multiple cointegration and error correction by Smith and Harrison. This paper also is available in the net. You can have a happy reading of this also. So in this case, we have multiple cointegration. That is the drunk with her dog, and the dog with the drunk, then the drunk with her boyfriend, and then the drunk and the dog with the boyfriend. So we have multiple cointegration cases. So these cases I have already told you. Now what we have to do is, suppose we have two variables yt and xt, and there is a relationship between yt and xt given with this. Now if this ut, that is yt minus beta xt, is stationary, that is if it is I0, then we can say that yt and xt are cointegrated. So the system will be in the long run. So that in the long run, the average value of ut will be 0. So that yt will be equal to beta xt. We have the long run equilibrium. Okay, now, so here we have the equilibrium error, the equilibrium error.
Sir,
come on.
Can you just go to the previous slide?
Which one? This one?
Sir, please hold for a second. I'm just writing it down. Sir, please.
Okay. So here I am telling that we have two non-stationary variables yt and xt, and if a linear combination of yt and xt, the linear is I0, then there is cointegration between yt and xt. The linear combination we will get like this, that is ut equals yt minus beta xt. Okay, so in the framework of a regression, this means that first we regress yt on xt, get the residuals. The residual we are getting from this. That is the original value of yt and the estimated value of yt. That is beta xt. So we are getting the residuals. So if the residuals are stationary, then yt and xt are cointegrated. And this beta is called the constant of integration. And this particular equation is called the cointegrating regression or cointegrating vector. Okay, shall I continue?
Yes, sir.
Yeah, okay. So here we have the equilibrium errors. The equilibrium error is a stationary one. So one way to test if there is a relationship between non-stationary data is to find if equilibrium errors return to 0. If long-run relationship is there, then the errors must be a stationary series and they have a 0. Okay, this already we have seen. This we have already seen. See, the concept of cointegration was introduced by Granger in 1981 and Engel and Granger in 1987. Also explained the concept of integration, and then this cointegration is used as a statistical property to describe the long-run behavior of economic time series. This we have already seen. Now, how can we distinguish between a genuine long-run relationship and a spurious regression? We need a test for that. That test is the cointegration test. So the cointegration test we have in different formats. The most popular one is the single equation residual based test given by Engel and Granger. Then we have a Durbin-Watson cointegrating regression test, but this is very rarely used This is not available in any package also. Then the first one we can augment with the augmented angle creature test. Then we have a system method. The system method is given by Johansson and Jusselius. Therefore, this test is known as JJ test. This is a likelihood ratio test. We have two tests here, the trace test and the maximum eigenvalue test. I shall tell about the JJ test in the context of the package. Then that is during our workshop. And here I will tell you about the augmented angle creature test. That is the residual based single equation test. So for the residual based test, what we have to do is this. After estimating the model, we save the residuals from the static regression. That is, we use the level variable yt and xt, get the residuals, and consider whether the residuals are stationary. So we can have the classical method of plotting the residuals and getting the ACF, the correlogram. And in this case, the residuals appear to be stationary because the ACF, all the ACF are within the 95% confidence interval. The correlogram, both the correlogram and the plot show that the residuals are stationary. So that is the classical one. Then we can do it with the uniroot test also. So we have the three steps. Test that both the variables have the same order of integration. That is, say that they are both I1. So now, one precondition for the Cointegration test is that we should have the same order of integration for all the variables. All the variables that we consider must be either I1 or they all must be I2 and so on. So the order of the cointegration must be the same. That is one limitation of this sort of the JJ test, as well as not only the JJ test, as it is so with the residual based single equation test also. So all the variables must have the same order of integration. So this we can do with the uniroot test. Now estimate a long-run relationship by ONS. That is with the level variables, and then get the residuals and see whether the residuals have a unit root. If the residuals do not have a unit root, then that means if they have a unit root, that means there is no cointegration. If there is no unit root in the residuals, then we have the case of cointegration. So this is how we do the residual based tests. So here I am ending the discussion. The JJ test and all other things I shall show you during the workshop. Thank you.
And any any questions from this? Yeah.
No, I think before that we have something else. So I am just recapping everything. So most of the macroeconomic variables are non-stationary. If we have a non-stationary problem, the consequence is that we are getting spurious regression with the level variables. We have two approaches, classical and model. The diagnosis for non-stationarity for the classical one is the ACF test, that is the correlogram. Then, of course, we have some statistical tests also for the classical methods that I haven't taken up. For the modern one, we have the uniroot test. Then the solution for the classical one is differencing. For the modern one, of course, we use the differencing, but mainly we use cointegration. If cointegration is not possible, then we go for the difference. Then the estimation procedures are, for the classical, we have the ARIMA modeling or the Bose-Jenkins methodology, and also we have multivariate ARIMA modeling suggested by Harvey. That is ARIMA. Then on the other side, modem, we have a large number of cases. We have VAR model suggested by Sims, the US one. Then we have the VECM, Vector Error Correction Model, suggested by the London School of Economics, Sargent, Davidson, and Henry, and so on. And also, Henry has the London School of Economics methodology called GETS, that is general to specific methodology. So we have these methodologies in general, that is the general to specific model, the LSE approach or the Henry David's approach. Then we have the vector auto-regression model VAR suggested by Sims, and this was the dominant approach in the USA one time. Then we have the VECM, and this follows the Granger representation theorem, and VECM was the dominant approach used in the European continents in general earlier, and there was very heated exchanges, controversy between the USA econometricians and the European econometricians one time over the superiority of VAR or VECM. A large number of articles are there on this particular controversy. So I'm stopping here.